Its trademark name is Kinetic sand. It sticks to itself and little else. It does not dry out. It flows like a liquid, but it can be molded into hard, solid shapes. And its unique properties capture the attention and imagination of people of all ages. It can keep kids' attention for hours, and yet parents love it because it never dries out and it's very easy to clean up. So what is kinetic sand made of, and how does it work? Well, as the name suggests, the primary ingredient is sand. Good old regular silica sand. Its chemical formula is SiO2, a silicon atom connected to two oxygen atoms, and it makes up 98% of the entire mixture. Now, certainly the properties of pure sand are different than kinetic sand. So what's in this mysterious 2%? Well, the short answer, silly putty. Technical answer, polydimethylsiloxane. This is what it looks like. How can so little of this stuff transform regular sand into such an interesting substance? Well, to answer that question, we need to think like atoms. So it helps to picture polydimethylsiloxane, or PDMS for short, like a long snake with silicon, oxygen, silicon, non-organic belly, and an organic, nonpolar, scaly surface made up of methyl groups, which is a carbon atom with 3 hydrogens pushing outward. The silicon atoms are very large compared to the carbon and hydrogen atoms nearby. They're large enough to draw electron density away from the hydrogens, creating slight polarity, and thereby providing the possibility of hydrogen bonding. Now combine this with the fact that in the silicon-oxygen belly, each oxygen also has lone electron pairs. This means there is slightly negative electron density sitting out there just longing for some fun interaction. Consider also that the PDMS polymer is very flexible, so the molecules are able to move around so that the most ideal interactions occur. This means that as PDMS chains get close enough, they shift their parts around in ways that allow for many possible multiple hydrogen bonds. Let's talk a little bit about hydrogen bonds. These are intermolecular interactions. They're not an actual chemical bond. They're definitely an interaction that causes molecules to stick together. However, in general, hydrogen bonds are much weaker than chemical bonds and can be easily broken. Now consider also the sand. Silicon dioxide bonds are extremely flexible as well, and there are all of these oxygens with their electrons also just begging to join the party. And then, unlike carbon-hydrogen tetrahedra that are locked into their angles pretty rigidly, the silicon-oxygen tetrahedron angles that are formed in this matrix of silicon dioxide, these tetrahedron angles can also be of varying angles, varying measures, and so they're very flexible, and they also orient themselves in a way that allows for the formation of more hydrogen bonds. And then because the sand particles are so small, we can imagine that these interactions are very weak. But the closer you bring the material, in other words, compact it, the harder it will be, because more of these hydrogen bonds are able, or perhaps forced, to form. And then as it's pulled apart, the weight of the sand particles overcomes the attraction of the hydrogen bonds, and the molecules separate easily, flowing almost like a liquid. Okay, let's leave the world of atoms now that we've got a pretty good idea what's going on here. The question remaining is this: why 2%? We certainly know what pure sand acts like. It doesn't stick together at all. And we know what pure silly putty acts like. Why is 2% the magic mixture number? Try to imagine what would happen as you move from 2% silly putty to 1.5% to 1 or maybe 0.5%. Now also try to imagine what would happen if you added more of the dimethylsiloxane. Once you've come up with your hypothesis, it's time for you to run your own experiments. See what different mixtures get you, and most of all, have fun and stay curious with this mysterious, addictive substance. Some other interesting related topics that you could explore: non-Newtonian fluids, viscosity, and rheological properties.